If you're like me, you might have wondered what it would actually look like if you could fly through the entire solar system to see it with your own eyes. And while I hate to spoil it right away, but what you're seeing in this rendered animation I'm showing you is not what you would see if you could somehow fly through the solar system. And there's several reasons for that, the most obvious of which is that the camera right now is traveling a lot faster than the speed of light, which, as far as we know, is completely physically impossible. And, well, the speed of light is only about 300,000 kilometers per second, whereas the solar system from the sun all the way out to Neptune is about 5 billion kilometers. So it takes several hours to get all the way out there. But I don't want to make this video several hours long, most of which would just be staring out into the blackness of space, looking at, admittedly, the beautiful stars, but without being close to a planet, because the distances are much greater than the sizes of the planets. There's another reason, though, which is that you might see that as you go past all these planets, you can actually see their surfaces quite clearly. And that's because I'm doing this in Blender, where I can set the lighting however I want to. And in this render, it's been set up where the lighting is just constant, right? I just put in a light and I tell Blender to make the intensity the same regardless of where something is in the sort of virtual solar system here. But in reality, the sun is the source of almost all the light in the solar system. There's some light from the other stars in the galaxy and even from other galaxies, but most of the light you can actually see anything by is from the sun. And of course, as you get further from the sun, well, the intensity of sunlight is going to drop. So in reality, if we go back to the sun, well, starting at the sun, first of all, we wouldn't be able to actually see these sort of, local variations in brightness across the surface of the sun like this, right? Instead, it would just, well, first of all, if you look directly at the sun from, this close, you would just go blind. In fact, if you look directly at the sun for more than a couple seconds here on Earth, you'll go blind. So there's no way we'd be able to distinguish the sort of, bright and dark pieces, but you can do with, a very sort of sensitive instruments that see small variations of brightness, and you can also with a proper setup that has good filters to reduce the intensity of the sunlight. You can see things like sunspots with not the naked eye, but with a telescope that has a proper solar filter on it. To be clear, do not ever point a telescope at the sun unless it has a proper solar filter on it. For the same reason, you should not look at the sun without wearing eclipse glasses or welder's glass or something like that. So the sun is just going to look solid white though, and the camera can't go blind, but it won't be able, it will just saturate, right? And we can see no variation because, again, we want to sort of, as much as possible, simulate what we see with our own eyes, but of course, the monitor can only get so bright, and pixel values are only recorded up to a maximum of just being solid white. So we'll just set all the pixels, just crank up the brightness until all the pixels are solid white, and then we'll make a proper light source that acts like the sun, which is not the text. The texture you're seeing there is what they call an emission texture. It's not the actual light source. You can't, strictly speaking, see the light source because of the way that Blender does things. So, or the way any rendering software does things, really. But it's co-located with this textured model of the sun. So if we fly back out to Mercury, though, now, first of all, Mercury is a lot closer to the sun. So rather than seeing this, sort of vague approximation of the, brightness at the surface, which looks kind of like if you look at the moon, actually, it would look more like this, right? Where it's very bright and it's, still possible to see features. It's not going to completely wash out or blind you. You could be on the surface of Mercury and look down at the surface, and if you could avoid, the overheating from the sun, you could look down at the ground without going blind. And if you were in orbit around Mercury, you could look down at the surface and be able to actually see things, but it would be very bright like this. So next up, if we fly out to Venus, then, well, it's not going to be that different than it was with the constant lighting, because I set the level of the constant lighting to match the level of lighting that we have at Earth, because of course that's what our eyes are adapted for, is the level of light that we have at Earth, because that's where human beings live, at least for now. I don't know if we'll ever sort of, travel to or, sort of permanently live on other planets, but for the foreseeable future, it's the only place we live is Earth, which is why we got to take care of it. And of course, it's also where we evolved, so it will always be our home. But at any rate, Venus just looks solid white for different reasons, which is that Venus, of course, is permanently covered in clouds of sulfuric acid, amongst other things that sort of vaporize and form clouds there. And so it just looks more or less solid white with these slight variations from changes in the clouds. And this is the only planet here that I am using a procedural texture for, rather than using image textures that come from telescopes and from various space probes that have been launched, mostly from NASA. Although I got some of the image textures directly from NASA, and most of them I got from a website that I'll link that has free image textures of all the planets. It's actually fairly nice that they give those away for free. So, anyways, if we move on to Earth, we are going to see pretty much exactly what we saw before, because, like I said, I calibrated that constant lighting to match the level of lighting that it should be at Earth. So nothing really changes when we go from the constant lighting to the actual accurate lighting for Earth. And then if we fly further out to Mars, well, now this is where the sunlight starts to decrease in intensity, but it hasn't changed that much, because Mars isn't that much further out than the Earth. Earth is 150 million kilometers from the sun, and Mars is something like, what, 200 something, yeah, 230 million kilometers from the sun. So it doesn't change that much. And it's not until we now fly out to Jupiter that we start to really notice a difference. But Jupiter is like 800 million kilometers from the sun, so it's, several times further out than Earth. And in addition to that, when you get further away from the sun, the intensity of sunlight doesn't drop off linearly; it drops off, quadratically, with what we call the inverse square law, right? So if we get twice as far from the sun, it's not half as bright; it's a quarter as bright. And if we get three times as far, it's not a third as bright; it's one ninth as bright, and so on and so forth. And this is true for any light source, right? As you get away further away from a light source that emanates in all directions, the light is sort of being spread out over an area that goes up, like the square of the distance, and so therefore the intensity drops off like the square of the distance. So at Jupiter, it looks, a lot fainter than the images we typically see. And there are several reasons for that. One is that the images, of course, are taken with cameras, either on telescopes or on space probes. And those cameras are sort of, set up to take those images. And we adjust things like the exposure time to match the level of light that we expect. Also, if you've looked at any of these objects, including Jupiter, through a telescope, you might notice that they appear quite bright. You might also notice that when you look at Jupiter in the night sky, it appears as sort of a single point to the naked eye, but it also appears quite bright. That has to do with a subtlety of how optical systems work, which I will maybe do a separate video on and explain in the future. But the short version is just, when you're looking at something, really far away and it looks like a single point like that, all that light is kind of being condensed to a single point. So kind of imagine that going to like a single little spot inside your eye, versus when you're up close, it's the same amount of light that's hitting Jupiter, but now you're able to see it across a wide part of your field of view. So it's being spread across more of your eye or across more of the camera. Um, and there's more to it than that, but that's kind of the short version. And so, and that's one of the reasons that good telescopes need large mirrors, is to gather lots of light from distant objects, so that when we actually want to resolve an image of that object, we have a reasonable level of brightness for each sort of individual pixel in the image. At Jupiter, though, if we were looking at it with our naked eye, like from orbit around Jupiter, it would look kind of like this, right? So you could still definitely see it, and you could see features on it pretty well. And in fact, if you were sort of, sitting in a nice, dark room with a good viewing window in your spacecraft, after you let your dark vision get adapted, you could probably see it quite well. It would actually make for probably quite a nice viewing experience if you could find a way to fly all the way out there, and also if you could be in a this close of an orbit to Jupiter without having problems with the radiation, which are both just technological problems that are in principle solvable. So now, The next planet that we will visit, though, is Saturn. And when we get out to Saturn, that's where it starts to really get dim, right? Jupiter was dimmer than we expected, but you could still definitely see things, and you could even be able to see without sort of your night slash dark vision adapting. And as a result, you'd be able to see color quite well. Once you get out to Saturn, that's where we get to the point where it's really getting dim, and you could definitely see it, and it would actually probably make for quite a serene and otherworldly experience to sit in front of a window in a spacecraft orbiting Saturn and look at it with your adapted dark vision, because it would still be dim, but your eyes would adapt and you'd see all the stars there, and I'm sure it would be incredible. I hope that someday we're able to fly out there and do exactly that. But one thing right away is you'd actually barely be able to see the rings, at least until your dark vision adapted. And even afterwards, they would be a lot harder to see than they are in telescopes and cameras. Because again, we're just using the naked eye, but imagining if we could fly out and see it from up close. So it would be again, you could actually see details in the gas clouds of the actual planet body, and you would be able to see the rings, but they'd be a lot harder to see than they are in normal images. So next up, if we fly out to Uranus, and I will sidestep the Uranus versus Uranus debate, which I think actually based on like I don't actually speak Greek, but based on knowing the Greek alphabet, I think it would actually be pronounced more like Uranus. If anybody speaks either classical or modern Greek, feel free to let me know. So at any rate, Uranus, or however you want to say it, there's more than one way to anglicize a word, right? So I guess if let's just anglicize it as uh, Uranus for now, right? When we get all the way out there, that's where it would start to get pretty difficult, even with your dark vision adapted, to actually see details of the planet. And you wouldn't really be able to see that sort of green color at all with the naked eye. I mean, you'd maybe be able to just barely make out that there is a green hue to it, but it would definitely be fairly difficult. And this is getting to the point where it's almost easier to tell the planet is there by the fact that you can't see the stars behind it than by seeing the reflected sunlight off of it. And so finally, if we go out to what is, I guess, currently the last official planet of the solar system, Neptune, by the time we get out to Neptune, it is almost impossible to see anything on the surface, right? You can just barely. Um, the only reason you can kind of see a feature is basically because the contrast in the image texture is a little bit higher than it probably is in reality. But nonetheless, this is getting out to the distance where it's really hard to see anything, and it is definitely much easier to tell that the planet is there by the fact that there's something covering the stars than it is to see the reflected sunlight. So if we could somehow do this grand tour out through the solar system, we would be looking at the surface of Mercury, and it would be very bright and almost a little bit blinding. Venus would be just a little bit brighter than we expected. Earth would look pretty much exactly like it does. Mars would look a little bit dimmer than we expect. Jupiter would look substantially dimmer than we expect. Saturn, it would make for, I think, probably the coolest viewing experience and would be very otherworldly. You'd barely be able to see it, or barely be able to see details, I should say. Um, and then when you get out to Uranus, it would be you could barely see anything. And you get out to Neptune, you can barely see anything. And then finally, if we are going to include the dwarf planet Pluto, which I guess you could argue if it still counts as a planet or not, right? It's these things are more of human definitions, right? There is sort of objective reality to it all, but a planet is a word that we humans use to describe something, and so the underlying physical reality is that there is a rocky body out orbiting in the outer solar system. Whether or not you want to call it a planet is a matter of subjective debate. But by the time you get out to Pluto, there's basically no way you could see anything, right? The sun is so far away at that point, and the sunlight is so dim that you really would only be able to tell that it's there by just sort of uh, seeing that you can't see the stars behind it. And of course, in images from the New Horizons probe, well, that's a camera that has very sensitive detectors that are one designed to capture very weak light, so they're sort of made to be sensitive. And two, of course, they use a longer exposure time, whereas you can't really adjust the exposure time of your eye. I mean, your body can adjust that to some degree, but not in the same way we can adjust the sensitivity of sort of semiconductor camera arrays. So, anyways, this is at least sort of in terms of light intensity, what you would see if you could fly out through the solar system. I will maybe do a video in the future on why it does look so bright when you look at something through a telescope, or when you look at like, for example, when you look at the moon with your naked eye, it looks really bright. But then, of course, if you're standing on the surface of the moon, it definitely is fairly bright. But it's not as sort of, like if you look at the moon at night, it's almost like your eyes hurt a little bit if you look at it for too long. And that's again because all of that light from the entire moon is getting collected down to a relatively small area in your eye. And again, that's also why you can see Jupiter as this bright sort of, point of light in the night sky. It's because all that light is going to one point in your eye, versus if you're up close, it's the same size of object, but that light is now going to, uh, you know, spread over a wide area of your eye, and you're looking at different parts of it with the naked eye. So I'll maybe talk about that more in the future. Although that's a pretty much is the reason right there. So, anyways, I like to sort of think about things like this, and I kind of uh, you know made a Blender render when I was first learning to use Blender, and kind of noticed how hard it was to see the outer planets. So I thought I'd make a quick video about this. So, anyways, thanks for watching.